Welcome to Constellations, the podcast from Kratos, where industry leaders share their thoughts and experience on the future of space business, policy, and opportunity. If you like Constellations, please support us by giving a rating and review on iTunes. And don't forget to share this podcast online to help our community grow.
Welcome to Constellations, the podcast from Kratos. My name is John Gilroy, and I'll be your moderator. Our guest today is Bulent Altan, Chairman and CEO of Mynaric. During today's podcast, we will discuss laser terminal technology as a market disruptor, the adoption of laser across the global space network, and how its implementation will impact the future of space communications. To go over this fascinating topic, we have invited Bulent Altan, CEO of Mynaric, a new company innovating laser communication terminals for ground, air, and space. Bulent, let's first talk about the landscape of global network technologies. Can you tell me briefly about some of the currently available technologies for communication?
John, first of all, thank you very much for having me in your podcast. Really honored to be here talking about the constellation and the optical communications and its impacts to the whole constellation push as we see it. Since the dawn of the wireless communications, radio frequency-based communications have been the dominant, if not the only major way of communicating some reasonable amounts of data. These RF-based communications have given us anything from radio to early broadcast TV, aviation and maritime communication for our civil, military, and government needs and such. First, they were analog in nature, but over time, with the advent of digital technologies, the overlying communication on RF also became digital, giving us now capabilities such as Wi-Fi, cell networks, and much more. These applications in large are to stay, and RF-based technologies is well suited for these wide area and wide geographical coverage situations. And it is here to stay for these kind of applications. Optical communication using lasers, though, has been in use for some time now and giving us point-to-point communication. As one can imagine, not all communication needs to be sender and a whole group of receivers scattered over a large area. Just like in wired communication, also in wireless, we have cases where we need to communicate between 2 points with very high bandwidth, high security, low power and mass, and also immunity towards jamming through adversary means. This is where laser technology has been utilized in the past, similar to like our use in fiber networks. And the terrestrial implementations have been simple, not over too vast distances so far, limited very often by the limitations also in horizon, and therefore have been simple to implement. Yet as we now build networks which span more than just the surface of Earth, as we look into networks covering airplane usage, airborne usage, stratospheric usage, and also space, and building constellations, optical communications now has to cover vast distances and reliably needs to connect fast-moving objects. And this is where free space optical technology like the one from Mynaric is coming in, and companies like Mynaric are developing.
In previous interviews, you've drawn a parallel between the early days of the internet and what's going right now in space. And so think this is really valid? You think your children look back and go, well, hey, my dad was in the second wave or something, huh?
Absolutely. I think the parallels to the internet are quite immense. If you think about it, when we started the internet, it was thought about first of all, as a military communication that connects multiple nodes in a resilient way in case certain nodes do go off. And it was really DARPA today that made ARPANET back in the day. And it's over time evolved into this resilient network that connects pretty much everything in the world as we speak today. And that networking really brought with it a tremendous use case from what used to be computers now to PCs and handheld devices. Now we can't really think about anything not connected. In a backdrop like that, we believe that space-based constellations will play a big role in now getting into places where having that wired communication is not possible. It's not feasible. Digging trenches and laying cable, whatever, fiber or copper, is not really cost effective. And that's where space is going to play a big role. And optical comms will be building the backbone of it.
Bulent, among the prominent disruptors entering the global communications market, laser terminals seem to be at the forefront. Can you please explain for the general listener out there what a laser terminal is, please?
Of course. So what we understand under a laser terminal, or more accurately named free space optical communications terminal, is a device which simultaneously transmits and receives a laser beam over long distances and uses that outgoing laser beam to communicate vast amounts of data to the communication partner, and it uses that receiving beam to receive data from it. In the crudest form, it would do that by turning on and off that laser, which we call on-off keying, to modulate data onto that laser beam. And you can do tens of gigabits a second of communication that way. Going beyond that, when you want to achieve hundreds of gigabits, it does then use more advanced modulation techniques to communicate that, send that laser beam with data modulated onto it over those vast distances, achieving hundreds, if not hundreds of gigabits of data, connecting two satellites, two airplanes, a satellite and a ground station, different communication nodes. What makes these terminals unique is their dynamic nature. The terminal can accommodate very fast motion. If you think about satellites, these things are traveling at 17,000 miles an hour. It can accommodate high levels of vibration such that the vibration doesn't take the laser beam away from the communication partner. And it does all of that in a very high speed and while still keeping that low power and high security characteristic.
Bulent, I know you have an advanced degree from Stanford University, and you could go toe-to-toe with mathematicians on this, but just say you're talking to the regular, maybe even a software developer in the Midwest somewhere. And so could you share with us maybe how the technology makes laser communication work?
So besides generating a laser beam and then amplifying it such that it has enough power to reach a communication partner, possibly multiple thousand kilometers away in space, the main challenges go into that dynamic compensation that I just mentioned in the previous question. What makes laser communication very powerful is how narrow the outgoing beam is, which results in most of the energy used landing on the communication partner's receiver. This allows a very energy efficient communication. But this also means that even tiny vibrations can cause the laser beam to veer away from the communication partner, and that the movement of, for example, a satellite can cause it to leave the incoming beam's area. That means that both terminals need to track each other very accurately, multiple orders of magnitude more so in RF-based technologies, and keep the beam concentrated and staying on each other. That means very accurate optics internal to the terminal. That also keeps that accuracy over vast temperature ranges, and extremely fast-moving mirrors that take out that movement, takes out that vibration, and a software system that controls all of it multiple hundred times a second. That really advanced control system is really the unique heart of what builds it, Mynaric and other free space optical terminals.
So last night I told my wife I was going to interview Bulent and talk about laser communications between satellites, and she said, wow, can you imagine the math involved in that? So there's positives and negatives to everything. So Bulent, what are the pros and cons of laser communication versus the current available communication technologies?
As in any technology, optical communications is a complementary technology to the existing ones. As such, it isn't here to replace radio-based communication, but enable new cases, or maybe in certain cases where RF is falling short, take over those. The main advantage of optical communication is the immensely higher throughput, very high security due to the fact that it is not omnidirectional, meaning it doesn't go everywhere, but only to the communication partner physically. So it can't be hacked. It can be interfered with. It is also not possible to go ahead and jam it. In today's world, we see radio-based communications being jammed quite frequently by adversarial forces. And what also is very unique about optical comms is its low power usage and size. To put all of this into numbers, for the same amount of power and mass that we build our terminals today, if we compare what is being used in space for an inter-satellite link, if you look at RF technology, you're getting about 6 to 8 megabits a second with the same power and size. Now, when you compare to our Mark III terminal, we get 100 gigabits a second. So the changes in throughput are tremendous. But of course, there are places where optical comms isn't a perfect fit. In communication use cases which go through the atmosphere, clouds can stop optical communications as they would stop the light transmission. This is something to take into account for these unique cases. Secondly, optical communication implementations are point-to-point today. Though there are multi-point communication technologies for optical comms in preparation, they are still many years out. And this means in order to cover a wide area, you need to use radio frequency. So an example of a communications constellation satellite, the connection that the satellite would have to the ground to thousands of users, like for example, a OneWeb or a Starlink satellite, that would be done in radio frequency. But that same satellite, for its point-to-point communication to a neighboring satellite or to a gateway or a ground station, would use optical communications, concentrating that thousands pieces of communication from multiple users into a single laser beam and handing it out. That's the reason why we say we built the backbone of these constellations.
You just mentioned the speed of the transition and the size of some of the transition here. What about the types of data? Is this one type or all kinds of types, or what does that role in this discussion have at all?
So our terminals and the underlying technology is built to be easy to use and transparent to our customers. When our customers use our terminal and when a link is established between the two communications nodes, the complexity of keeping the beam onto each other and taking out the vibrations and motion, all of that is to a certain extent hidden from the customer. And for the satellite, our terminal really looks like a simple cable between the two satellites. That really allows an easy implementation using the networks, the protocols, the infrastructure that we built on the ground to do communication exactly in space as well. So you hand off the data and we carry it over just like a cable would, and we try to make it as easy on you as possible. That means any kind of data can be transmitted over our terminals over those multiple thousands of kilometers. In our Condor Mark III case, that's up to 8,000 kilometers, and our in our larger case, the Condor MEO terminal, out to 40,000 kilometers in distance, those 100 gigabits, and the underlying data can be anything. That is, I want to say, one of the big elements of making sure that this technology can penetrate all these networks. We make it easy to use for our customers, really mirroring what has been done on terra firma, also in aviation and in space, making sure that the internet as is does not need to be reinvented at all, but can be used also in space networks.
Bulent, thousands of people from all over the world have listened to this podcast. Go to Google and type in Constellations Podcast to get to our show notes page. Here, you can get transcripts for all 100 plus interviews. Also, you can sign up for free email notifications for future episodes. Bulent, this is the Constellations Podcast, so I got to ask a question about networks here, What global communication network applications can laser terminals be used for?
So the immediate application, of course, that comes to everyone's mind are all these broadband constellations, these global broadband constellations that we all talk about. There are many of them out there, and if you try to count them, that would be way too many, and I don't want to forget anyone out there, but they have been growing quite rapidly, and these constellations are now talking about thousands and even tens of thousands of satellites getting broadband connectivity into every single nook and cranny of this earth. If you look into it today, when you have mobility cases, when you are in the plane, you're on a ship, when you are in not densely populated areas, when you're doing Internet of Things out in the North Sea, maybe doing wind farms, you need connectivity everywhere, and you need it very often in a broadband fashion. And these are constellations that really build and close that digital divide that exists between densely populated areas and not so densely populated areas. These are the constellations we enable today. That's really the first use case we can think of. But it doesn't just stop there. There are many other constellations out there. If you look at it, there are hundreds of Earth observation satellites out there, some of them forming real constellations. And our optical communications technology can also connect Earth observation satellites with each other, forming a mesh network in the sky, making sure that the latency from the time image is taken to the time it is transmitted to the end user is taken from hours today to just seconds. By having a mesh network, a satellite that does not have a ground station in view can take the data it just gathered from its Earth observation sensor and hand it over to a neighboring satellite, and that can hand it over to the neighboring satellite until the data arrives at a satellite with a ground station in view and can downlink it. I think this in itself will bring yet another revolution in Earth observation. First revolution being the constellations, like the ones of planets, and now with the synthetic aperture radar and high spectral imaging constellations. And the second revolution coming with us, the real-time nature of the communication. Besides that, there are other applications that we see as well and we support today. For example, relay satellites. Relay satellites are satellites in a higher orbit that allow singular satellites to bounce their data off of these high-flying satellites and then back to ground stations, again, enabling low-latency communication rather than having to wait for a ground station to appear. Of course, we are seeing a lot of military and government networks for communication in areas where there is adversarial powers doing radio frequency jamming. Optical communications offers a very advantageous solution, not just in bandwidth, but also in resilience and also geolocation, because very often you lose your GPS capability. And then we are seeing also some longer term use cases, such as orbital outposts, new stations being talked about, both in Earth orbit and beyond, but also computation centers that are looked to be put in orbit, which require tremendous connectivity.
Well, Bulent, I'm taking notes here, and so are many of my listeners, and I'm running out of ink here. I got IoT, Earth observation, SAR, I got image, I got comms, I got relay. I got to find a new pen here or something. So usually you look at all these applications. So which applications really has the highest growth potential?
Well, I think if you look at the numbers, of course, the communications constellations, the broadband constellations have the numbers. Today, when you look at what the number of satellites are in space, just a little bit more than 2 years ago, it was less than 2,000 active satellites in orbit. And it was really the communications constellations, the broadband constellations, that more than doubled that number in a short amount of time. And that trend is only going to continue and increase. So our number one customer base is, of course, the communications constellations. Each one of these satellites needs multiple of our terminals to build a mesh network in the sky. Very often they host 4 of our terminals to allow that satellite to talk to the satellite to the front, to the back, to the left and right, really making beautiful, that orthogonal mesh network around the sky, really sending data efficiently in each direction. And when you multiply that with the number of satellites being launched, that is a tremendous number of terminals. And that, again, is the reason why Mynaric's focus has been to make these terminals so cost effective and mass produced. And those two parameters are so important to our customers, especially in this, because for a communications constellation, the need is in the tens of thousands of these terminals very soon in a year.
Bulent, we've touched on this kind of, on the edge here of the conversation, security. And I'm in the Washington, D.C. area. You've got the DoD up the street here. We got to talk about security here. You've mentioned that the signal can't be jammed, but, my research shows that, I think when you use radio frequency, people can detect that with a laser communication that's not detectable. So that puts you at an advantage in some ways in a defensive posture, don't you? So it can't be hacked. You can't even see if you're transmitting. So this is very desirable for people in the intelligence community or Department of Defense, I would assume.
Absolutely. I think radio frequency communications have come a long way, and there are amazingly intricate antennas that are state-of-the-art, that concentrate most of the energy towards the communication partner. But even then, there is rest energy going into every direction, and these can be detected by an adversarial detector. That means you give away your location. And then, of course, if your adversary knows which frequency you're communicating on, it can use that frequency to transmit a much higher power signal to jam your communication. Optical is different. Optical goes really only in the intended direction. The beam is very narrow and therefore cannot be picked up by anyone else but your intended communication partner. And that means security. When you're doing satellite to satellite communication, your communication partner is not going to be jammed from another angle through an adversarial force. Or when you're doing ground station communication, the intended photons, really the beam, is going to land just on your ground station and just a few meters around it. And I think when you're operating an optical ground station, if someone pitches a tent and puts a giant telescope right next to yours, a couple of meters away, you'll recognize that.
Bulent, I know you spent some time in L.A. Last time I was in L.A., I saw a lot of Teslas. And my big conclusion is that you really can't have electric cars without charging stations. And you really can't have, laser communications without something on the ground. So what infrastructure is necessary on the ground to support laser communication terminals?
I think as far as infrastructure goes, it's really at the start of the value chain. It is companies like Mynaric that have to exist, that focus on mass producibility and cost efficiency of these terminals. The data sets are there. When you look at Earth observation, when you look at the communication constellations today operating are, for example, Starlink and OneWeb, you realize that the data demand is there. These satellites generate a tremendous amount of data that require to be moved over vast distances. So the demand is there. It's really the production infrastructure that has to happen. And that's where Mynaric, I think, is unique in the fact that we have invested over the last couple of years into building a factory that can build thousands of these terminals a year, into researching technology that makes, for example, this precise optical instrument out of metal, with really off-the-shelf machining equipment that allows mass manufacturing in a cost-effective manner. And all of these had to happen so our customers can rely on a manufacturer like Mynaric, so they can baseline it in their constellation. All of that was investment ahead of the demand curve that Mynaric has put in place, and we show that infrastructure that we have built both here in Germany, but also in the US in our LA facilities to support our customers. And only when they see the infrastructure and the investments that we have done do our customers really realize the potential here.
You know, Bulent, I mentioned electric cars. There's a lot of challenges with making a transition to electric cars. We know that. But there's also challenges in migrating to laser technology. So what are the main challenges to the technology, and how can they be mitigated?
In most cases, when we look at the satellite technology today, and I have already said, when you look at a broadband constellation, the data volume is there. Those thousands of communication links down to the end user generate a tremendous amount of data, but that needs to be stitched together into a stream that can be given to our optical communications terminal. What we have on Earth are fantastically complicated and very powerful switches, these networking equipment that can deal with this tremendous amount of data. The analog of that has to happen also in space, and these switches aren't that easy to deploy in space. But we have seen now the first cases of them. But still, generating hundreds of gigabits of data, digitally switching them and sending them into the right direction is the upstream challenge that our customers have today. But we see broadband constellations living up to that challenge and exactly doing that.
So we're going to go from some of the practical challenges of applying this technology. We're going to go up to about 40,000 feet, maybe not to Leo, but about 40,000 feet here. So from a global perspective here, what are the most important aspects or impacts of the expanded use of laser terminals to the world and humanity? What
laser terminals are doing is they are being the enabling technology behind these constellations. And our first use case is, of course, these broadband constellations, these global broadband constellations. And if you think about communications in the world today, there are the haves and the have-nots. The economy has been very digitally driven, and people in large cities that are well connected have an advantage in being in the workforce. We've seen this more so in the COVID crisis over the last 2 years. We've went away from the offices and are all at our homes doing remote working. And there we've seen the capability differences that exist between people. And if you look into that, we need more capability across the population, not just half of it, but all of it. And if you can solve the digital divide that exists between people who have access to broadband and people who don't, we're going to see less migration to cities. We're going to counter the mega cities mega trend. We're going to ensure that there is an equality between different geographies and that anyone can be a part of the global digital economy. We will see people from different parts of the world being part of crowdsourced campaigns and crowdsourced work. Today, when you're, for example, looking to build a logo for your company, you normally do a competition online, and we're going to see people respond to these competitions from the smallest villages in the most remotest areas of the world, because we will be able to get broadband there. So we will make out of the digital divide a digital unite for the whole world.
Another big question here for you, Bulent. I'm going to wrap it up here. So what do you hope for the future of mankind in space overall?
Well, now been in the space business for about 2 decades, and I've played many roles from rockets to capsule to satellites, and now the underlying communications technology. What I really want out of the space technology is being an enabling technology for everything we do. We've seen this with the internet. We see the fact that the internet hasn't just changed the computer industry; it changed the way we work. And I expect the same thing with space technology. It will be an enabling technology for many things we do. As we are here on Earth, it's going to make life on Earth better. Earth observation will contribute to our understanding of climate change. Communications, as I said, will unite us digitally across the globe and will connect everyone. It will ensure for security across our borders. But also, as humanity goes beyond, of course, beyond Earth, I think optical communications will also play a big role there as we have more and more instances of human settlements across our solar system to connect. And I think I see that future definitely happening. Mankind is here to explore, here to settle, here to expand. And I think very, very often we will see the Earth-Mars communication. Whenever that comes, I think it's going to be optical.
I'm trying to come up with a summary from our listeners, what we've learned from this interview today. And I think there's 3 words that I've taken away from this interview is optical communication can provide speed, deliverability, and agility. I think that's a good 3-word summary here. I'd like to thank our guest, Bulent Altan. He is the chairman and CEO of Mynaric. Thank you.
Thank you very much, John. Thanks for giving me the time.
Thanks for listening to Constellations, the podcast from Kratos. If you like this interview, please subscribe, tell a friend, and give us a review.